It's a great pleasure meeting you all in another video. In this video, I hope to discuss with you all on what is elasticity in detail. We know solid substances are made up of molecules, and these molecules have interactions between them. We call them intermolecular forces. So these intermolecular forces are very much stable at a particular distance between these two molecules. If you try to increase the distance between them, they become unstable, and if you try to decrease the distance between them, then also they become unstable, and they want to return back to a much stable state, that is over here. So if you apply a force, they will create a restoring force to restore the initial length. So simply, that's elasticity. If you apply a force along this direction, it should increase the distance between these two molecules. So it has increased the distance, right? Then its stability has gone down. To regain its stability, it will create a restoring force. That's why once you remove this applied force, this restoring force will get back the original intermolecular distance, because they were much stable at this distance. Now you must having a better idea on what is elasticity and what results elasticity. Now let's look at what is strain and stress. What is strain? The Greek alphabet epsilon is used to denote strain. So strain is E over L. E is the extension and L is the initial length. Just look at this. We have two molecules. If you apply a force F, let's say its initial separation was L, and due to this force, it has extended by E. Now let's see what will be the scenario if you apply the same force in between three molecules. Like this, you have a molecule over here, another molecule, and another molecule. Now when you apply a force F to these two molecules, you must understand, if you draw this setup in a free body diagram, you will have something like this. The applied force downwards, and here you will have another force, and this force will pull the other molecule downwards, and this is the other applied force. So now you must be able to see that you have applied the same force on either directions. Here the length is L plus E, and this length is L plus E. Therefore the total length is 2L plus E, 2L plus 2E. This is an important idea. Then the strain is equal E over L. Let's say you have a rod of length L, and if you apply a force F, the elongation would be X, and then if you calculate its strain, that would be X over L. Now let's consider a wire of length 2L. Still you are applying the same force F. Now the elongation would be not X but 2X. If you calculate the strain, you will have 2X over 2L, so that's X over L. So if the same force is applied where the cross-sectional area and the materials do not differ, but the length only differs, then there is no change in strain. Have this idea in your mind. This would help you to understand the question we are to discuss finally. Now let's talk about stress. Let's go through an example first, so you should understand better why do we consider stress. I have a wire of cross-sectional area 2A and cross-sectional area A. Now let's assume you are applying a force of 5 newtons for both the wires. Now the applied forces are the same. On wire A and wire B. Although the forces are same, do you think you have the same outcome? No, right? Here the outcome is going to be a larger strain. Here the outcome is going to be a smaller strain. So it seems like talking of the applied force is pointless. Let's consider something new. Now, what is stress? Stress is force over area. It will give you the information of force acting per unit area. Let's consider this area as 1 meter cube for now. Then you will have 2 meter cube area here. In the first case, you will have 2.5 Newton of force acting per meter square and 5 Newton of force acting per meter square in the second case. So this should give you a better idea. Here, just look at the stress. 5 Newton meter is higher than 2.5 Newton meter minus 2. The 5 Newton per meter square is going to have a larger strain than 2.5. Now you must understand why we choose to talk about stress instead of force, instead of the applied force. Next, let's look at the elastic and proportional limit. Let's consider a material that shows the following stress versus strain variation. So stress is given by sigma and strain by epsilon and shows the following variation. When you load, it increases like this. Let's say when you load, it increases like this. And when you unload, it chooses the same path and returns back to 0. This is what you call the elastic character. Now it is within the elastic limit. There is no any permanent deformation. Then what is proportional limit? Most of the materials, a straight line portion within the elastic limit is observable, where the stress is proportional to strain. Then the limit at which the proportionality is no longer, you call that as the proportional limit. And just little above, you will have the elastic limit. Elastic limit is the maximum stress you could apply where there won't be any permanent deformation. And the proportional limit is the maximum strain at which stress is proportional to strain. When you apply a larger stress, there is a maximum stress where if you apply beyond that stress, the atoms or the molecules will dislocate. These molecules will break and form other bonds. There is a permanent deformation. Now you must have an idea. The elastic limit is the maximum stress. That could be applied to have the maximum strain that will return to 0 once the applied force is removed. If you apply beyond this, a permanent deformation is observed. Let's say you apply a force F, extension of delta is observable. Now, if you apply stress beyond this, there is a elastic and a plastic deformation. Once the applied force is removed, it should have returned back to this length, but instead, a permanent deformation is observable. Let us try a question from the 2000 past paper. According to this question, a uniform wire of length L attains the proportional limit once mg is suspended. The length of the wire is reduced to L by 2. And they stress it's the same wire, okay? Therefore, there is no change in the area. Now, we must find with what mass being hung, it will reach proportional limit. To attain the proportional limit, maximum strain that won't have a permanent deformation, we could find it as x over L. As we have discussed previously, when the length is decreased to L by 2, to have the same strain, the extension required is E by 2. Therefore, the maximum strain is E over L. Now, to attain this strain, let's find what is the required stress. So, we know the relationship between stress as stress is equal Young's modulus time strain. The strain is the same, Young's modulus is the same, therefore the required stress is also the same as before. That is, stress is force over area. We have mg over a in the first case. So in the second case, there is no change in the area. Therefore, the required force remained as mg. Now, what if the question was something like this? When a mass m is hung, if it reaches proportional limit, length of the wire is L and area is A. When this wire is replaced with this wire made of same material but length L by 2 and area 2A, what is the mass that should be hung to attain proportional limit? Let's approach with this similar idea. So maximum strain is E over L. To attain this strain, what is the required stress? So that is, stress is equal Young's modulus time the strain. They have the same strain, same Young modulus. Therefore, the required stress is also the same. In the initial case, the stress is force over area, and that is mg over A. In the second case, it's m dash g over 2A. So let's simplify for m dash. So you have m dash, that's equal to 2m. So if the question was something like this, then you would have required a mass of 2m to attain proportional limit. I hope this video should have given you a lot of information. If so, don't forget to share with your friends. Thank you.